List terms of finite sequences or list n terms of infinite sequences. Well, one way to define a sequence is that it's an ordered list of numbers. Another way to define it, it's a function whose domain is the set of positive integers. So if I take a look at this sequence 2, 4, 6, or 2, 4, 8, 16, 32, you can say, well, what could it represent? Maybe a website starts, and on the first day of the month they get 2 hits. Second day, 4 hits. And they keep doubling the number of hits for, say, 31 days. If you were going to write out this sequence, you would write out the terms much like we have here. And just for notation, we would say the first term would be a sub 1, and that would be 2. Second term would be a sub 2, and the third term would be a sub 3, and so on. And so very quickly we see, if we look at the subscript, we can see which term we have. Well, this is where the notion of a function with a domain of positive integers come in. I can call my function a sub n equals 2 to the n. We use a real different notation. Like you and I are used to f of x equals 2 to the x. That's when x is any real number. But with sequences, to alert the reader that you have a sequence, you don't do the of x like that. You go a sub n. Oh, it's a sequence. Now, when you go ahead and find the formula of the sequence, you want to say that formula is going to be set up in a very specific way. And that way is where the first term is going to be governed by putting that input of 1 into your function. And 2 to the first is what? 2 to the first is?
2.
2. And so if we see if this formula works, we would then put a 2 into the input area of the function. We get back what? We get back?
4.
4. And if we put a 3 in, we end up with what? 2. 2 cubed, which is what? Which is
8.
Which is 8, and it does seem to work just fine. This website was doing pretty well because by the 31st day, I guess we'd substitute in a 31, and they were getting about 2.1 billion hits.
Wow.
Yeah, that's pretty good. Yeah, so it may not be practical, but here's the thing. We want to look at 2 types of sequences. One is finite, one is infinite. And when I look at a finite sequence is nothing more than a sequence whose domain is the set of the first n positive integers. In other words, your domain would be 1, 2, 3 out to 5 or something. And that would generate 5 outputs, like we see right here, finite. The actual numbers that you see, the 2, 4, 8, 16, 32, these are the terms of the sequence. And we don't really call it a function. We say the explicit formula defines the nth term. It may sound messy, but we use that terminology with sequences instead of functions. And lastly, we could have an infinite sequence that continues out forever. And we show that by just putting ... Let's see if you got it. Spot quiz, kiddo. All right? What we're going to do, we as you, right? We as you. We're going to go ahead and see if we can list the first 5 terms of this sequence. And I'm going to do the first, and you're going to do the next 4. B sub 1 is found by taking 3 times, and n here is 1. So 3 times 1 plus 4. And that's what? That's
7.
7. And what I need to make you aware is that we're just substituting in that subscript for where we see n in the formula. Substituting in that subscript for where we see n in the formula. That's all we're doing.
Okay.
I do 1, you do 4. That sounds fair to me. So if I go ahead and take a look at b sub 2, what would the calculation look like?
It would be 3 times 2 plus 4.
Very good. And so that's, I want to say that's 6 plus 4, which is?
10.
10. How about b sub 3? What would that be?
That would be 3 times 3 plus 4.
Very good. And that would be what? That would be?
13.
13. And you can kind of eyeball the rest of them. B sub 4 would be 3 times what? 3 times?
3 times 4 plus 4.
Very good. And that would be?
That would be 17.
Okay. So, yeah, because it would be 12 plus 4?
16.
Very good. And the very last one would be 3 times what? 3 times?
3 times 5
plus
4.
15 and 4 is?
19.
So there are the first 5 terms, and I would list them as terms. Bracy, that's how you list them. 7, 10, 13, 16, 19. You'd list them. Finite or infinite sequence?
Finite.
Finite. Let's do one more. What's factorial mean? What's factorial mean? What's factorial mean? If I say 3 factorial, what are you multiplying?
I'm not sure.
It's 3, and then you start subtracting by 1 times 2, subtract 1 until you get the 1. So 3 factorial, well, that'd be 3 times 2 times 1. 5 factorial, well, that would be 5 times 4 times 3 times 2 times 1. 10 factorial would be 10 times 9 times 8 times 7 times 6 times times 4, times 3, times 2, times 1. So what we're going to do again is list the first 5 terms. I'll do 1, and you do 4. That sounds fair. C sub 1. 1 factorial, that's just 1. Okay? All over 1 squared plus 1. Again, what are we doing? We're taking this right here, which is the subscript 1, and we're placing it where we see the n. That's what we're doing. Just like function notation. And the hardest part is evaluating it, but this is just 1 plus 1, which is?
Would that be 1 over 2?
1/2. Very good. There's my first term. C sub 2, what does the calculation look like?
Would it be 2 factorial?
Good. Over
2 squared plus 1?
Very good. So 2 factorial, that's 2 times 1. 2 squared plus 1 is 4 plus 1, which is 5. There's my second term. For the third term, what would the calculation look like? Because that's what's key here.
That would be 3 factorial.
Very good. Over what? Over what?
Over 3 squared plus 1.
Very good. Now 3 factorial is 3 times 2. And 3 squared plus 1 is 9 plus 1. I want to say this third one is 3/5.
Yeah.
Basically, we're done here. How about the fourth term? What would the calculation look like?
4 factorial over 4 squared plus 1.
Very good. 4 times 3 is 12. And 12 times 2 is 24. Is that right?
Yeah.
So we got 24 over 16 plus 1. And for the very fifth term, that would be what? That would be
5 factorial.
over what?
Over 5 squared plus 1.
Very good. And 5 factorial would be 24 times 5, basically, which is 120, all over 25 plus 1, 26. And if I divide them both by 2, I get 60 over 13. Easiest question of the day. I want to write these 5 terms. I put a what? What is that thing called?
A bracket.
Almost.
A braces.
Bracy, good. And the first term is?
1/2.
Second term?
2/5.
Third term?
3/5.
Fourth term?
24 over 17.
And then we'll just write in the last term, which I know is 60 over 13. Thank you.
Let's write an explicit formula for the nth term of a sequence. So the first sequence has the terms -2/11, 3/13, -4/15, 5/17, -6/19, and so on. Now, we'll begin by looking for a pattern, and there are actually 3 patterns that we notice. The first is just noticing in the numerator that the values go from 2 to 3 to 4 to 5 to 6. Now, each of these numbers will be 1 more than the previous number. So what does that is 1 times n. So then I think to myself, if n is 1, 1 plus something is 2. If n is 2, 2 plus something is 3. If n is 3, 3 plus something is 4. So I think to myself, what would that value have to be? Well, 1 plus 1, 2 plus 1, 3 plus 1 would give me 2, 3, 4. So the first pattern I recognize is that I generate the numerator by the expression n plus 1. Now let me look at the denominator. For the denominator, each of these terms, 11, 13, 15, 17, 19, differ by 2. So what does that is 2 times n. So let me look at the 11. 2 times 1 plus a number equals 11. Let me look at the 13. 2 times 2 plus a number is 13. Let me look at the 15. 2 times 3 plus a number is 15. What does that number have to be to generate each of these denominators exactly? Well, 2 plus 9 is 11, 4 plus 9 is 13, 6 plus 9 is 15. So it looks like the denominator is generated by the expression 2n plus 9. Very last thing I need to do is to be able to alternate the terms of the sequence, and they need to alternate from negative to positive to negative. So what does this is a multiplier. If I take -1, I'll either raise it to the n or the n plus 1. If I raise it to the n, when n is 1, the first term is negative. when n is 2, the second term is positive. So there's my multiplier. Now I can go ahead and write out the explicit formula for the nth term of this sequence. The explicit formula for the sequence a sub n is equal to negative 1 to the n times n plus 1 divided by 2n plus 9. Now let me turn to the second sequence, which has the terms negative 2 over 25, negative 2 over 125, negative 2 over 625, negative 2 over 3,125, negative 2 over 15,625. And again, we're looking for patterns. And again, I'm looking for 3 patterns. Let me look in the numerator first. I notice all of my numerators are the numbers 2. So I know I'll put a 2 in my numerator. Now let me look in the denominator. I notice all of my 2's seem to be the result of taking 5 to some exponent. 25, well, that's 5 squared. 125 is 5 cubed. 625 is 5 to the 4th, and so on. So now I realize my common theme is that I have a base of 5, and the exponents 2, 3, and 5 differ by 1. So I know that 1n will make each of these terms differ by 1. So I think to myself, 1 plus what number is 2? And then I go to the second term. 2 plus what number is 3? Go to the third term. 3 plus what number is 4? And I very quickly realize that number is 1. So my denominator is generated by a base of 5 raised to the n plus 1. Last pattern may be the easiest to ascertain. Notice each of these terms is negative. So each of these terms will be a negative number. So let's go ahead and write out the explicit formula for the nth term of the sequence. We have b sub n is equal to, and again all the terms are negative, the numerator is always a 2, and the denominator is 5 raised to the n plus 1.
Find terms of recursive sequences. Sequences like this Fibonacci sequence occur in nature. They will occur in growth patterns of things like nautilus shells, pine cones, and tree branches.
Did you know that the longest pine cone ever was like 22.9 inches?
Actually, no, I didn't.
Yeah.
It seems like it should be larger.
That's like...
All right, maybe not. All right. The way this Fibonacci sequence is constructed is constructed different than what we've seen in the past. What we do is we base a term on the previous term or terms. In other words, to construct the Fibonacci sequence, I start with 1 and 1, and then I add 1 and 1 to get the next term, which is 2. Then I add 1 and 2 to get the next term, which is 3, and add 2 and 3 to get the next term, which is 5, and so on. So what is diagnostic about this type of sequence is that it is based on the initial term or terms. You could be given more than one. Those have to be given to you. And some equation that enables you to use these preceding term or terms. And this type of sequence is called a recursive sequence. So we want to write the first 5 terms of this sequence defined recursively. So I have to give you a starting point. I could give you 1 or more, but I give you a starting point. Here the starting point is what? Go ahead and look up there. A1 is?
3.
All right, so I know my first term is 3. Then when I take a look at when I have my formula, what I'm seeing for the nth term, what I'll do is I'll take 2 times the previous term, n minus 1, and then simply subtract 1. And I'll do this for n greater than or equal to 2. In other words, I'll start on the second term. So let's go ahead and generate the first 5 terms. A1 we know. First term is our starting point. That's what? That's
3.
3. Now the way this works is A2 becomes the second term. And the way the formula works, it says take 2 times the previous term, which is A1, and subtract 1. So that would be 2 times what? 2 times?
2 times 3.
Very good. Minus 1, which is 6 minus 1. That's what? That's
5.
5. Good. Well, let's go ahead and generate the next 3 terms in a like manner. For A3, again, I'll take 2 times the preceding term, which is A2, and subtract 1. So I just go to the preceding term and substitute it in for A2, and the preceding term is?
5.
So I have 2 times 5 minus 1, and that's what? That's?
9.
9. Very good. 10 minus 1. I'm up to the 4th term. I'll take 2 times the preceding term. That'd be A what? A sub?
A sub 3.
Minus 1. Then I'll substitute in A sub 3, which we just found to be?
To be 9.
So I have 2 times what? 2 times?
2 times 9 minus 1.
And what is that? That's what? That's?
17.
Beautiful. And finally, we get up to the very last term, and the very last term is the 5th term. So the 5th term is found by taking 2 times, which term? 2 times the?
17.
Well, the preceding term, which would be the?
Oh, that would be A sub 4.
A sub 4 minus 1, and you'll substitute in for A sub 4 now?
17.
17. And 2 times 17 minus 1 is?
33.
Beautiful. So when we write out our first 5 terms, we can do that. We'd write the first term, which is what? Which is?
3.
3. Second term, which is?
5.
Third term, which is?
9.
Fourth term, which is?
17.
And the last term, which is?
33.
Beautiful. Thank you.
Write the first 5 terms of the sequence defined by the recursive formula shown below. A sub 1 equals 9. A sub n is equal to 3 times A sub n minus 1 minus 20. And this is for values of n greater than or equal to 2. Now with the recursive formula, what you have to realize is that for any given term, A sub n minus 1 refers to the term before A sub n. So we can start listing the first 5 terms immediately. We know A sub 1 is equal to 9. A sub 2 is equal to 3 times the term before it, A sub 1, minus 20. Well, the term before it is 9, so I have 3 times 9 minus 20. And that's 27 minus 20, which is 7. Well, for the third term, A sub 3, this is 3 times the term before it, A sub 2, minus 20, which would be 3 times, now the term before A sub 3 was a 7, minus 20, and that gives us 21 minus 20, which is 1. Let's go to the fourth term. This would be equal to 3 times A sub 3, the third term, minus 20. This is 3 times the third term, which is a 1, minus 20. And 3 minus 20 is negative 17. We get to the fifth term, A sub 5. This is 3 times A sub 4, the term before the fifth, minus 20. Which is 3 times, now the term before the fifth term is the fourth term, that's negative 17. So 3 times negative 17 minus 20. And this gives us negative 51 minus 20, which is negative 71. So if I want to write out my first 5 terms, I can do that. I would have 9, 7, 1, negative 17, and negative 71. These would be the first 5 terms of the sequence defined by the recursive formula that is shown below.
Find explicit formulas for the nth term of a sequence. What we're going to do is we're going to take a sequence, which we know is a function. The domain is the natural numbers, 1, 2, 3, and so on. And we're going to go ahead and see if we can start with the terms and end up with the actual formula, the explicit formula that would generate the terms. And because we do have a function here, if we took a look at 2, 4, 6, we have to imagine what would we have to do to generate a 2, 4, 6 if we put the inputs 1, 2, 3 into some function. Well, in this case, it's pretty easy. You're just kind of doubling those numbers.
Yeah.
So that means my explicit formula, A sub n, is equal to 2 times n. So when we do this type of thought process, we have to ask ourselves a few questions. And the questions are, do the terms differ by the same amount? Like here, they differ by 3. Or is there a number you can multiply by to get from one term to the next? Things you're looking for to generate the function's formula. Do you see evidence of perfect squares or perfect cubes? Are there alternating signs, plus, minus, plus? If there are fractions, you'll generate a formula for the numerator and denominator differently. That means you'll generate a function by looking at the numerator with one expression and the denominator with another. And again, if the terms all have exponents or bases, can you find a pattern there as well? So the very first type of sequence I see has 10, 13, 16, and what strikes me is that all these numbers differ by
3.
By 3. So 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9. You're probably thinking, very good, Jay. But what I'm driving at is start by saying, okay, a sub n is 3 times n, and then ask yourself, if I go ahead and put a 1 into this calculation for n, what number would I have to add or subtract here to generate the 10? And that number would be what? It would be?
7.
7, very good. So that fills in the rest of the formula, doesn't it? 3n plus 7 is equal to an. Look at the third term. Let's do a quick check. We're not that busy. You look at the third term and you say, gosh, if I go ahead and substitute in a 3 for n, and then I add 7, that's 9 plus 6. That's what? That's
16.
As it should be. You look at b sub n and you say that's nearly the exact same situation. It's just you have alternating signs. So when you have alternating signs, the thought process is to first generate the formula, which we did. That's 3n plus 7. And that will generate the absolute values of the terms, the 10, the 13, the 16. Then to alternate the sign, to go from positive to negative and back again, you multiply by either negative 1 to the n or negative 1 to the n minus 1. And the way you decide which one it is by looking at the first term. In this case, the first term is positive. So negative 1 to the n would give me negative 1 to the first for the first term, which is negative. But negative 1 to the 1 minus 1 would give me negative 1 to the 0, which is positive. So this tells me my exponent will be, I'm just going to write this in right here, negative 1 raised to the n minus 1. Now we want to go ahead and take a look at terms and generate the explicit formulas, and we're going to be seeing 4, 9, 16 in the very first sequence. These are what? These are perfect squares. And the only thing we have to be careful of is that we want to put a 1 into the calculation, yet it looks like we want to square 2. We want to put a 2 into the calculation, yet we want to square 3. We want to put a 3 into the calculation, yet we want to square 4. So what are we looking at doing every time we put a 1, 2, and 3 into the calculation?
Would you add a 1?
We'd add a 1 before we would square it. Very good. For the last of these sequences, I want to realize that I have 3 pieces of information to look at. First is I have alternating signs. When you have alternating signs again, you're going to multiply by either negative 1 to the n or negative 1 to the n minus 1. And the way you make the decision is you say that first term, is it positive or negative?
The first term's negative.
Very good. When that's the case, remember you're substituting a 1 for n. Negative 1 to the first is negative 1. So that begins d sub n. d sub n is equal to negative 1 to the n. Then I'm going to draw a fraction bar. So we're just going to ask ourselves, if n is 1, I want an output of a 1. If n is 2, I want an output of a 2. If n is 3, I want an output of a 3. What would the numerator be?
Would it just be n?
N, it'd just be that value. And for 5, 10, 17, I'd say, well, gosh, what's the pattern here? Do they differ by the same amount?
No.
No. And if I was to give you a big old hint, I'd probably say something like, have you seen numbers close to them before? 5, 4, 10, 9, 17, 16.
Yeah.
Yeah. These numbers, 5, 10, and 17, are all one more than
being a square.
Than being that 2 squared, 3 squared, 4 squared. So all we do is we take our formula to generate 2 squared, 3 squared, 4 squared. Which was what? Which was what? Which was?
N plus 1 squared.
And we just add what? Add?
And then just add 1.
Add 1 to it. Thank you.
Let's write out the first 5 terms of the sequence defined by the explicit formula shown below. And the formula is a sub n is equal to negative 3n plus 8. So what we'll do is we'll go ahead and substitute in values for n of 1, 2, 3, 4, and 5. And we'll find the corresponding first, second, third, fourth, and fifth term, respectively. So let's begin. When n is equal to 1, this will enable us to find a sub 1, which is our first term. We'll take negative 3 times that same 1 plus 8. And that's negative 3 plus 8, which is 5. Well, when n is 2, this will enable us to find a sub 2, which means we'll take negative 3 times n, which in this case is 2, plus 8. And that's negative 6 plus 8, which is 2. Moving on, when n equals 3, this will enable us to find a sub 3, which is our third term. So the calculation would be negative 3 times that same 3, plus 8, and that's negative 9 plus 8, which is negative 1. When n is 4, this will enable us to find a sub 4. The calculation would be negative 3 times that same 4 plus 8, and that gives us the calculation of negative 12 plus 8, which is negative 4. Rounding out our fifth term, n would be equal to 5. This will enable us to calculate a sub 5. We'll take negative 3 times that same 5 plus 8. And that's negative 15 plus 8, which is negative 7. Writing as a sequence of terms, we put a brace, and we'll write the first term as 5, second term is 2, third term negative 1, fourth term negative 4, fifth term is negative 7.